4.5 billion years ago, Earth did not exist. There was only a swirling cloud of gas, dust, and icy particles, the remnants of a long-dead star. This cosmic debris, stirred by gravity and time, began to collapse inward. At the center, pressure and heat built up until a new star ignited, the Sun. Around this newborn sun, material continued to spin, forming a massive protoplanetary disk. From this disk, the early planets, including Earth, gradually took shape. But these early worlds were not solid or stable. They collided, broke apart, reformed. These impacts generated intense heat, melting rock and metal. Earth began as a ball of molten chaos. Its surface was a violent inferno, with temperatures soaring beyond 1,500 degrees Celsius. The air was thick with carbon dioxide, nitrogen, and sulfur. Thunderstorms raged endlessly. Volcanoes poured lava across a crust that barely existed. As Earth continued to spin, its internal materials began to settle. Heavier elements, primarily iron and nickel, sank toward the center. Lighter silicates rose to the surface. This process, known as planetary differentiation, created Earth's layered structure: an iron-rich core, a semi-solid mantle, and a rocky outer crust. But how did the dense iron core truly form? Two main theories exist. The first is centrifugal sorting. In this view, rotation alone was enough to pull heavy materials to the center, like a natural centrifuge. The second theory involves late-stage bombardment. According to this model, Earth was repeatedly struck by iron-rich meteorites. These metallic intruders melted into the early Earth and contributed to the growth of the core. Both theories remain under debate. The truth may lie somewhere between. What is certain, however, is that Earth's iron core eventually began to rotate independently from the mantle. This movement, combined with high conductivity, generated a powerful magnetic field. It was a silent revolution, unseen and unnoticed, but critical. Without this magnetic shield, the solar wind would have stripped away Earth's atmosphere long ago. The planet might never have supported water nor life. It all began with dust and a spin. Part 2. Water fell from the sky. Earth's oceans did not begin as vast, deep basins. They arrived from the sky. In the planet's early days, relentless meteor showers bombarded its molten surface. Many of these meteors carried ice, frozen water from the outer reaches of the solar system. As they crashed into the hot Earth, the ice melted and vaporized. Over millions of years, enough water accumulated to form the first oceans. But these were not the oceans we know today. They were shallow, volatile, and far saltier. Constant evaporation, volcanic gases, and dissolved minerals created a chaotic mix, dense, acidic, and restless. Within this primitive ocean, something extraordinary happened. Alongside water, the same meteorites brought complex organic molecules. Amino acids, basic building blocks of life, were delivered in trace amounts. It was not life, but it was potential. These molecules began to interact with Earth's own chemical environment. Volcanoes were everywhere, erupting into sea and sky. When fire met water, heat and pressure transformed everything. The clash of lava and ocean generated dynamic zones rich in energy and chemistry. It was here, on the edges of boiling vents, within scalding tidal pools, near underwater eruptions, that early Earth became a laboratory. No human planned it. No theory predicted it. But the planet itself began to experiment. As lava cooled, the first islands formed, tiny landmasses of black rock protruding from the sea. Rain fell, lightning struck. Ultraviolet light bathed the surface. The elements mixed, broke apart, recombined. In these early waters there were no continents, no life, no order. Yet the conditions were just right for reactions to begin. Earth's oceans, hostile, unstable, and wild, served as the testing ground for what would eventually become life. It was not a miracle. It was chemistry, time, and chance on a planetary scale. Part 3. When life rose from the foam. Roughly 3.5 billion years ago, life made its first visible mark. Cyanobacteria, primitive single-celled organisms, appeared in the shallow waters of early Earth. They didn't move, they didn't hunt, but they could do something unprecedented: photosynthesis. By capturing sunlight and releasing oxygen as a byproduct, cyanobacteria transformed the chemistry of the planet. Over time, their waste, oxygen, built up in the oceans and eventually leaked into the atmosphere. What was once a suffocating sky, rich in carbon dioxide, slowly shifted toward something more breathable. They left behind evidence: stromatolites. These layered rock-like structures, still found in parts of the world today, are fossilized colonies of cyanobacteria. In them, we see the first visible architecture of life. But how did life begin in the first place? That remains one of the most enduring mysteries in science. There are several competing theories, none confirmed. One of the oldest is spontaneous generation, the idea that life could emerge from non-living matter at any moment. This belief persisted for centuries until Louis Pasteur's 19th century experiments conclusively disproved it. Life, he showed, does not arise without cause or process. Another hypothesis is panspermia, that life or its building blocks came from space. Meteorites may have delivered amino acids, sugars, and even dormant microbes to Earth. It's an idea that shifts the question, rather than answers it. If life came from elsewhere, where did it begin? Then there is the primordial soup theory. In this model, Earth's early oceans were a chemical broth. Lightning, ultraviolet radiation, and heat triggered reactions that created complex molecules. In laboratory simulations, scientists have reproduced many of these results, including the spontaneous formation of amino acids. A fourth theory focuses on deep-sea hydrothermal vents. There, intense heat, pressure, and mineral-rich fluids could have created the right conditions for life's chemistry. Even today, these environments host some of the most ancient and resilient organisms on Earth. Despite decades of research, no single theory has triumphed. We still don't know exactly where life began, or how many times it may have tried and failed before succeeding. But what we do know is this: life didn't begin as a grand organism. It began in silence, in foam, in chemistry. And once it started, it never looked back. Part 4. When the rocks began to move. As Earth slowly cooled, its surface began to solidify. What had once been a global sea of molten rock hardened into a crust, thin, fragile, and restless. This crust didn't remain still. Cracks formed, sections shifted. Over time, the planet's outer shell fractured into massive, rigid slabs, tectonic plates. These plates float atop the semi-fluid mantle beneath, moving slowly but relentlessly, just centimeters per year. Yet over millions of years, their movement reshaped the world. The first known continent was Volbora, formed more than 3 billion years ago. It was followed by Rodinia, Penodia, and finally Pangaea. Each of these supercontinents came together through plate motion, then eventually broke apart again. This cycle of assembly, breakup, and reassembly is known as the supercontinent cycle. It's a defining feature of Earth's geology. And no other planet in the solar system shows signs of similar behavior. Tectonic movement creates mountain ranges, carves ocean basins, and triggers earthquakes. It explains the rise of the Himalayas, the rift valleys of Africa, and the volcanic ring of fire encircling the Pacific. Not all crust is the same. Oceanic crust is younger, denser, and primarily made of basalt. Continental crust is older, thicker, and composed mostly of granite. These differences matter. Oceanic plates subduct, sink beneath continents, recycling material into the mantle. Continental plates tend to ride over. Without this dynamic motion, Earth would be geologically dead. No mountains, no earthquakes, no volcanism. But more importantly, no renewal. Tectonic activity drives the carbon cycle, helps regulate climate, and plays a role in nutrient circulation. It creates the very landscapes where life can flourish. It's easy to imagine Earth's surface as stable. In truth, it is constantly moving, rebuilding itself from within. What began as still rock has become a planet in motion, and every continent we know today is just one moment in a much longer tectonic dance. Part 5. When Earth became a snowball. Around 700 million years ago, Earth froze. This was not an ordinary ice age. It was a total planetary shutdown. Ice reached the equator. Oceans turned to slush. From pole to pole, Earth was encased in white. Scientists call it snowball Earth. What caused it? Oxygen. As cyanobacteria and algae filled the oceans with oxygen, that oxygen reacted with methane, a powerful greenhouse gas. The result was catastrophic. Earth's natural insulation vanished. Temperatures plummeted. Global glaciation began. But even under kilometers of ice, life did not disappear. Below the frozen surface, hydrothermal vents on the ocean floor continued to pump heat and minerals into the water. Microbial life, already adapted to harsh conditions, held on. These survivors became the seeds for what would come next. Eventually, volcanic activity reversed the freeze. Carbon dioxide built up in the atmosphere. The ice began to melt, and when it did, the oceans changed. Glacial runoff flooded the seas with minerals and nutrients, phosphates, iron, and silicates. The result was a massive surge in biological productivity. Life, once trapped beneath the ice, now exploded in diversity. This sudden release of nutrients may have triggered the Cambrian explosion, a dramatic evolutionary leap that followed shortly after snowball Earth. In the span of just a few million years, multicellular organisms diversified at an unprecedented rate. Skeletons, shells, eyes, limbs, features we now associate with complex life, began to emerge. The snowball Earth event was not just a catastrophe. It was a reset, a harsh bottleneck that cleared the stage and opened space for innovation. Without it, life as we know it may have taken a very different path. Sometimes, evolution accelerates not in times of comfort, but in moments of crisis. Part 6. The Age of Fish and Coal Forests. Between 500 and 250 million years ago, Earth underwent one of the most profound chapters in its biological history. This span, covering the Cambrian, Devonian, Carboniferous, and Permian periods, saw the rapid rise of animals, plants, and ecosystems that would reshape the planet forever. It began with the Cambrian explosion, a burst of evolutionary innovation. These pioneers became amphibians, the first vertebrates to colonize land. With lungs and limbs, they opened a new frontier, one that had, until then, been the realm of mosses and fungi. At the same time, plants underwent their own revolution. Simple mosses gave way to towering ferns and seed-bearing trees. Vast swampy forests stretched across the continents. Over millions of years, these forests died, collapsed, and were buried. Pressure and heat transformed them into coal. These were the coal forests of the Carboniferous, a time when oxygen levels soared to nearly 35%, allowing insects to grow enormous. Dragonflies the size of seagulls, millipedes over 2 meters long, arthropods ruled the land and skies. It was an era of thriving ecosystems and dense biodiversity, but it did not last. At the end of the Permian period, Earth experienced the most catastrophic extinction in its history. Volcanic eruptions released massive quantities of greenhouse gases. The climate destabilized. Oceans became acidic and oxygen depleted. 95% of marine species vanished. Over 70% of land species followed. This event, the Permian extinction, reset life on Earth. It ended the age of coal forests, cleared entire ecosystems, and paved the way for new forms of life to emerge in the next chapter. It was both an ending and a necessary beginning. Part 7. dinosaurs ruled the Earth. From approximately 252 to 66 million years ago, Earth entered the Mesozoic era, an age defined by giants. Spanning the Triassic, Jurassic, and Cretaceous periods, this era marked the reign of dinosaurs and the rise of modern ecosystems. It began after the Permian extinction, the largest biological collapse in Earth's history. What followed was a reset. Life slowly returned, and a new group of reptiles began to diversify. These were the first dinosaurs. By the late Triassic, they walked the continents. Some moved on 4 legs, others on 2. Some were massive, others small and agile. They quickly spread into every terrestrial habitat. But dinosaurs were not alone. In the skies, pterosaurs, winged reptiles, took flight. In the oceans, massive marine reptiles like ichthyosaurs and plesiosaurs dominated the depths. Earth was teeming with reptilian life, adapted to every environment. Plant life also changed. Early in the Mesozoic, gymnosperms, non-flowering seed plants like conifers and cycads, became widespread. Later, in the Cretaceous, they were joined by a revolutionary innovation: flowering plants. These angiosperms used colorful blooms to attract insect pollinators, forming a new evolutionary partnership. Bees, butterflies, and beetles appeared. The ecology of the planet became increasingly complex. During this time, 2 small, inconspicuous groups evolved in the shadows of dinosaurs: birds and mammals. Birds descended from theropod dinosaurs, acquiring feathers and flight. Some early forms, like Archaeopteryx, show both reptilian and avian traits. Mammals also emerged: tiny, nocturnal, warm-blooded, and covered in fur. Though they couldn't compete with dinosaurs, they found niches in the undergrowth and darkness. They were survivors, quietly waiting. Then, 66 million years ago, it ended. A 6-mile-wide asteroid, now known as the Chicxulub impactor, slammed into what is now the Yucatan Peninsula. The blast was equivalent to billions of nuclear bombs. Fires swept the continents. Ash and sulfur darkened the sky. Photosynthesis ceased. Ecosystems collapsed. Massive volcanic eruptions in India, the Deccan Traps, added to the chaos. Within a geologic blink, 3/4 of all species vanished. The dinosaurs fell, but birds and mammals did not. And from the wreckage of that 5th mass extinction, a new story began. Part 8: The Rise of Mammals. With the dinosaurs gone, the Earth entered a new chapter, the Cenozoic era, beginning roughly 66 million years ago. This is the age of mammals. After the asteroid impact, the planet was transformed. Forests burned, skies darkened, food chains collapsed. But amid the destruction, a window of opportunity opened. Mammals, once small, nocturnal survivors, now rose to fill the empty ecological niches, with no large reptiles to compete against. They diversified rapidly. Some remained tiny, thriving in burrows and underbrush. Others evolved into giants. Over the next tens of millions of years, mammals spread across every continent. They adapted to every landscape and climate. Rodents, primates, hoofed grazers, canine predators, and aquatic mammals all emerged. From shrews to mastodons, from horses to tigers, the age of mammals took shape. But mammals were not the only ones to rise. In several regions, flightless birds became dominant predators. In South America and New Zealand, giant avian hunters, some over 3 meters tall, ruled the land for millions of years. These were the terror birds, fast and powerful, filling roles once held by raptors and theropods. Meanwhile, the Earth's climate began to cool. Polar ice caps formed, seasonal weather cycles intensified, mountain ranges rose as continents drifted. New landforms reshaped wind and ocean currents, triggering further climate shifts. These changes transformed ecosystems. Tropical rainforests gave way to savannas, grasslands, and tundra. Rivers carved valleys. Ice sculpted plains. As habitats changed, so did the species within them. Natural selection favored adaptability. Mammals continued to evolve. New forms, new strategies, new behaviors. The Cenozoic wasn't marked by a single dominant species, but by diversity. Life was no longer shaped by size and armor, but by speed, agility, intelligence, and cooperation. It was a world in motion, both geologically and biologically, and it set the stage for the emergence of something even more remarkable. Part 9, From Apes to Humans. The story of humanity did not begin with humans. It began with primates. Roughly 60 million years ago, small, tree-dwelling mammals known as Plesiodapus roamed the forests. They were not yet monkeys, but they had grasping hands and forward-facing eyes, traits that would prove essential. By 55 million years ago, a creature called Archicebus appeared. Light, agile, and insect-eating, it moved swiftly through the canopy. Soon came Eosimius, one of the earliest primates to resemble true monkeys. Tiny but advanced, it marked a critical branching point in primate evolution. Fast forward to 20 million years ago, the forests of Africa were home to Proconsul, a genus of early apes with traits shared by both monkeys and humans. From Proconsul came Dryopithecus, another arboreal ape, strong, social, and fruit-eating. Then came a breakthrough. Around 7 million years ago, a new form emerged, Sahelanthropus. It had a chimp-like brain, but its foramen magnum, the hole in the skull where the spine connects, suggests it walked upright. Bipedalism had begun. Over time, upright apes evolved into a series of increasingly human-like forms. Ardipithecus lived 4.5 million years ago. It still climbed trees, but also walked on two legs. Then came Australopithecus, short, strong, fully bipedal. One of its members, famously known as Lucy, walked upright through East Africa. Roughly 2.5 million years ago, Homo habilis appeared, the handyman. He crafted stone tools, simple but revolutionary. It was the first species in the Homo genus. Soon after came Homo erectus, a game-changer in every sense. Homo erectus stood then. 300,000 years ago, Homo sapiens emerged. Anatomically modern humans are direct ancestors, but we were not alone. Other human species coexisted: Neanderthals, Denisovans, and possibly more. We competed, interbred, and eventually survived. Neanderthals vanished around 30,000 years ago. Denisovans left behind only fragments and genes, but their DNA lives on. In us, our story is not linear. It is braided, complex, and unfinished. We are the last of many, but not necessarily the final chapter. Art 10, Life Never Stopped. 5 mass extinctions have already reshaped life on Earth. Each one erased entire branches of evolution. Each one reset the biological clock. And now, many scientists believe we may be entering a 6th. But this time, the cause isn't an asteroid or a supervolcano. It's us. Human activity has transformed the planet at an unprecedented pace. We've altered the climate, driven species to extinction, cleared forests, and filled oceans with plastic. Industrialization, warfare, and unchecked consumption have created a new geological force, one driven not by tectonics, but by thought. We are reshaping the Earth. And yet, we are also the only species capable of understanding what that means. We can study the past. We can model the future. We can choose. That choice is urgent because it took 4.5 billion years of cosmic accidents, chemical reactions, biological experiments, and evolutionary leaps to produce modern humans. The path was never straight. It was forged through fire, ice, extinction, and rebirth. And now we stand at the edge of another turning point. Will we protect what has taken eons to build, or accelerate its collapse? The truth is, life itself will go on. It always has. Life adapts, it mutates, shifts, and survives. It has survived ice-covered oceans, meteor impacts, and planetary upheaval. It doesn't stop. It evolves. If humanity disappears, life will continue without us. But if we endure, if we choose wisely, we may shape a new chapter, one where intelligence is not a weapon, but a responsibility. Because life never stopped, it simply changed form. Now, it's our turn to decide what shape it takes next.